This module, Module 1, which is the required basis for the electrical trades. It doesn't make a difference what electrical trade you're in. This is a must to know if you're going to be in it. This is Ohm's Law and Power Law Rules and Theories. This Module 1 is just a basic overview of series and parallel circuits. We'll be getting into more depth in series parallel circuits, series combination parallel circuits, and circuit analysis in modules 2, 3, 4, and 5, but for now this is just going to be a brief overview. We can think of voltage as being equivalent to water pressure. Amperage is equivalent to the flow rate of water. Resistance is equivalent to the restrictions. Think of a pipe size. If you have a small pipe, you're not going to get as big a flow through that pipe as you are in a bigger pipe. And then watts is equivalent to the amount of work that pressure and flow can do. Think of a water wheel. These are some of the rules for a series and parallel circuits. And the variables are E for voltage, I for current given in amps, R for resistance, and P for power in watts. In a series circuit, our voltage, total voltage, ET, is equal to E1 plus E2 plus E3. It's the sum of all the voltage drops to give me the total voltage. In a parallel circuit, though, voltage is the same everywhere. Total voltage equals the same voltage at E1, E2, E3, which is really the resistors. This ET is voltage, total voltage is the same at R1, the same at R2, the same at R3. Current is the opposite. In current, our total current in amps, IT, equals I1 plus I2 plus I3. In other words, if I measure my current at R1, R2, and R3, they will all be the same as measuring it at the total voltage source, RT. In a parallel circuit, IT is the summation. IT equals the current at R1 plus I2, which is the current at R2, plus I3, which is the current at R3. In other words, it's a summation. This current plus that current equals the total current. Our resistance in a series circuit is pretty easy. We just sum up the individual values of the resistors. R1 plus R2 plus R3 gives me my total resistance for the circuit. In a parallel circuit, though, we have this really looking scary equation, but later I'm going to show you how easy it is to do this equation. It is not difficult at all once you know some tricks with it. I know that electricians avoid this equation like the plague, and there are some tricks that you can use to get around it, but you should know how to do this mathematically. Our power in watts is P equals P1 plus P2 plus P3, and that's the same whether it's a series circuit or a parallel circuit. You may want to, by the way, on these rules, take the time, stop your video right here, and make a copy of these rules because you're going to be using them later on. Likewise here, these are the Ohm's Law wheel and Power Law wheel formula wheels for Ohm's Law and Power Law. Stop the video, make a copy of this. To use this, we have E, which is voltage, I is current, R is resistance. If I want to find E, voltage, in a circuit, and I know the amperage and the resistance, is E equals I times R. I cover up the E, I times R. If I want to find I, and I know E and R, I cover up the I, and it's E divided by R. If I want to know R, I cover up R, E divided by I. Likewise, in the power wheel formula, if I want to find P, I cover up P, it is I times E. If I want to find I, it is P divided by E. And if I want to find E, cover up E, P divided by I. The series circuit has only one path for current to flow. If one component burns out, all the components are turned off as current can no longer flow. Think of the old Christmas tree lights. If one bulb burned out, all of them were off, and you didn't know which bulb burned out. That's an important thing to remember. Here is a typical series circuit. I have 80 ohms, 80 ohms, 80 ohms, but these can be different resistance values, but in this case, they're all the same. And if you look at the circuit, in order to get from the plus all the way back to the minus, I must go through every one of these resistors. If one of these resistors burns out, there is no path for the current to flow back to its source, and all these resistors are off. Very, very important concept to remember in a series circuit. Here's the rules for series circuit again. E voltage is the sum of all the voltage drops. E1 plus E2 plus E3 equals the total voltage. But the current is the same everywhere. So IT equals I1 equals I2 equals I3. And resistance is the sum of the individual resistors. R1 plus R2 plus R3 equals RT. Power equals the sum of the different powers at each resistor. P1 plus P2 plus P3 equals total power. Looking at what we just looked at here, we had 120 volts and we had 380 ohm resistors. We can add these up because the resistance values is the sum in a series circuit. 80 plus 80 plus 80 equals 240, and I have 120 volts. Using the Ohms formula wheel, I have E divided by R is going to give me I. So 120 divided by 240 is going to give me 0.5. If you remember, amperage is the same everywhere in a series circuit. So I have 0.5 amps here, 0.5 amps here, 0.5 amps here. It's the same everywhere. Now I can find my voltage drops. I times R is going to give me my voltage. 0.5 times 80, 40 volts. 0.5 times 80, 40 volts. 0.5 times 80, 40 volts. If you remember, voltage is the sum of all the voltage drops. 40 plus 40 plus 40 equals 120. So I have all these values. I only have one more to find. 0.5 times 120 is 60 watts. 0.5 times 40 is 20 watts. Likewise, 0.5 times 40 is 20. 0.5 times 40 is 20. 20 plus 20 plus 20 equals 60. Series rules. Total resistance in a series is the sum of all the resistors. R1 plus R2 plus R3. R1 plus R2 plus R3 equals total resistance. Amperage is the same everywhere. And voltage is the sum of the voltage drops. 40 plus 40 plus 40 equals 120. And power is the sum. 20 plus 20 plus 20 equals 60. This is the rules for a series circuit. This matrix, you may want to make a blank page with a matrix that says E, I, R, P, and then we're going to label it the totals. R1, R2, R3, it could be R1, R2, it could be R4, or 5, or 6. It depends on how many components you have in a circuit that you're evaluating. A parallel circuit, on the other hand, has more than one path for current to flow. If one component burns out, all the components still remain, all the other components still remain on. Houses and businesses are wired in parallel. Think of it this way. At your house, if one light bulb burns out, the rest of your light bulbs are still on. This is an important thing. We don't want one light to go out, burn out, and then all of a sudden we don't know which light is out because they're all off like a series circuit. So houses and businesses are all wired in parallel. Voltage is the same everywhere in a parallel circuit, and this is very important because every electrical device we use requires a fixed voltage to operate properly. If you're plugging in a television set, it requires 120 volts no matter which outlet you plug it into. If you have a clock radio or stereo or any electrical device at all, even your stove stove, if it requires 240 volts and you have two stoves, they each have to have the same voltage in order to operate. Here's a diagram, a drawing of a typical parallel circuit. You notice that I can put a switch here and turn off R2 and R3, but I still have current flowing through R1. If R2 were to burn out, R1 and R3 still have voltage going through them and they're still working. If these were if these resistances were light bulbs, these two lights are still on, but R2 would be burned out. This is very important. This is a parallel circuit. Here we have supply of 120 volts. We have R1 is 40 ohms, R2 is 60 ohms, R3 is 120 ohms. So here's the rules for a parallel circuit again. Voltage is the same everywhere. Total voltage equals the voltage at R1 equals the voltage at R2 equals the voltage at R3. It's the same everywhere. Current, however, is the summation of all the currents. We have total current IT equals I1 plus I2 plus I3, which is the current across R1, R2, and R3 respectively. This is a scary formula. I know it is, but I'm going to show you later on how easy it is to do this. But there are also some tricks to get around it, but you shouldn't rely on it because it is very simple to do this formula. No matter how hard it looks right now, I will teach you how to do it easily. Power is the summation of all the power. P1 plus P2 plus P3 equals total power. The power at R1 plus the power at R2 plus the power at R3 must equal the total power in the circuit. Looking at that circuit that we looked at, in a matrix form, we had 40 ohms, 60 ohms, and 120 ohms. We can use this formula and come up with 20 ohms here. But with this matrix, it's a little bit simpler to just say, okay, I don't need to know what this total resistance is just yet. I'll calculate it another way, but I can find it by doing something very, very simple. I have 100, the rules now for a parallel circuit is the voltage is the same everywhere. So if I have 120 volts at the supply, I have 120 volts at R1, 120 volts at R2, 120 volts at R3. So I can take E divided by R to give me I. Looking at that formula wheel that I gave you for Ohm's Law before, told you to write down, E divided by R equals I. 120 divided by 40 equals 3 amps. 120 divided by 60 equals 2 amps. 120 divided by 120 equals 1 amp. And in a parallel circuit, the current is the summation of all the currents. 1 plus 2 plus 3 equals 6 amps. Now I can find this resistance using the Ohm's Law formula. 120 divided by 6 equals 20 ohms. 6 times 120, this is for the power, equals 720 watts. 3 times 120 equals 360 watts. 2 times 120 equals 240 watts. And 1 times 120 equals 120 watts. 120 plus 240 plus 360 equals 720. Resistance, looking at this formula, is the reciprocal of the sum of the reciprocals of all the resistors. This is 1 over R1 plus 1 over R2 plus 1 over R3. Later on you'll learn how to calculate this. Total resistance must always be less than the lowest resistor. Here the lowest resistor is 40 and I have 20, which is less than that. If you're calculating and you get a resistance value that's higher than the lowest resistance, then you know that you made a mathematical mistake and you need to recalculate. The amperage here, this is rules for parallel circuit again. Amperage is the sum of all the individual currents. Voltage is the same everywhere. And power is the sum of the individual component powers, and resistance is that formula I just showed you. Using the rules and a few simple formulas, we can calculate everything about a series or parallel circuit. At any point in a circuit, the total current entering the point must equal the total current leaving that point. For parallel circuits, it means that the sum of the currents in each branch must equal the total current of the circuit. Kirchhoff's voltage law. The sum of the voltage drops in a series circuit must equal the supply voltage. The rule sheet provided on slide number 3 concisely explains Kirchhoff's law, Ohm's law, and power law. A simple circuit, by the way, is a circuit with only one resistive component, one light bulb, one water heater element, one heating element for a stove or something, just one component. It's not a series circuit. It's not a well, it is a series circuit. It is also a series circuit as there is only one path for the current to flow, but we don't have to calculate the total current we would in a complex series circuit. The resistive values of individual components, whether a simple circuit or multiple resistors wired in series or parallel, never changes unless subjected to excessive heat. In other words, we were looking at resistors R1, R2, R3, and it was 40 ohms, 60 ohms, and 120 ohms in the parallel circuit we saw before. Those values at the individual resistors do not change. The total circuit resistance can change, but never the individual resistors. Total circuit resistance of a series or parallel circuit changes, but the individual component resistance remains the same. Voltage is the same everywhere in a parallel circuit. Current is directly proportional to voltage and inversely proportional to resistance. What this means is that as voltage goes up, current goes up. As voltage goes down, current goes down. Inversely, with resistance, and if the resistance goes up, the current goes down. If the current goes down, the resistance goes up. Current's directly proportional to voltage, but inversely proportional to resistance. This concludes the instructional portion of this module. In Module 2, we'll explore series circuits in depth. Be sure to click on the link below to take the online quiz. And remember to review this video as many times as necessary until you understand everything that's in it. This is kind of an overview of basics of what we're going to be discussing in the next 4 modules.